Hello, everyone. We're back with another episode of Computer Vision Talks. And today we're going to talk about Anna's work, which was accepted in ICCV 2021, that is Generalized and Incremental FewShot Learning by Explicit Learning and Calibration Without Forgetting. Anna was a research intern at Facebook, and she is a PhD at Max Planck Institute for Informatics. She took her MSc in computer science in Bonn University, Germany, and her BSc was from Russia. She has also been a research intern at INRIA Paris, and as well as at Uni Bonn with Hilde Cohen and Shuengal, if that's right pronunciation of their names, I'm afraid.
Yeah, more or less, yeah.
And probably we're going to talk about all the interesting topics combined today, incremental FewShot, right?
Yeah, that's true. It's my current topic, basically, which I'm working on my PhD. And previously, I was working, as you mentioned, at University of Bonn at INRIA. I was working on videos mostly, and it was video segmentation and video interactions, people interactions. So it's a lot of different topics. And now I'm actually going to talk about another topic. It's not connected to videos much, but it's also, I think, very, very interesting. So let me start. It's called Generalized and Incremental FewShot Learning by Explicit Learning and Calibration Without Forgetting. So first of all, I will my content, which I will cover today, what is FewShot learning? General, I think everybody, most of the people knows what is it, but anyway, I will introduce some details. Then I will extend it to what is generalized FewShot learning, because it's a more rare topic. And then I will talk about my framework, which we proposed for solving this task. And then I will also show why it is working and how it is working with ablation studies, and how it can be extended to incremental learning, because actually the two tasks, FewShot learning, actually generalized FewShot learning, is very connected to incremental learning. So let's start. What is it, FewShot learning? That basically we have a trained data and test data. Usually when you have supervised learning, you have a lot of trained data, you have like hundreds of samples per class, and then you can train your model that it can classify properly into new test data. FewShot learning means that you have very few training samples. You often have cases when you have only one training sample per class. For example, like if we look at only in the episode 1, then you have classes A, B, C, and then you want to classify test data into also this class A, B, C. But you only have one training sample per class. It means that you need to feed the model feed the model to this only few samples and classify. Why you have I have several episodes here. It means that you have several times you train on different training data on different sets of few samples, and then test them on their separate test sets. It means that you can have very good training samples, and then you will feed data and feed the model very well, and then your test accuracy will be very high. And sometimes you have very bad test samples, very rare cases. That's why it's important to have statistical correctness and have a lot of episodes. In the usual case that you test on 600 episodes, and then you have variation and your accuracy more accurate. So this is basically about the FewShot learning. Yeah, so you have a lot of different options. For example, one of the usual cases that you have, it calls N-way shot. N-way means how many classes, into how many classes you want to classify. 3-way means that you have 3 classes, and 5-way means 5 classes. So more ways means more difficult. And you also have, for example, more shots. It means how many training samples you have per class. So basically 5-way 5-shot means more training samples, more training data for each class, and it's more easy task. It's easier task. So what is a standard FewShot learning pipeline? That you have the data set, and you usually have some base classes, base training sets, which nobody talks about, but people use it to train the model. Basically, is the usual framework, it's meta-learning, where you simulate FewShot samples. And then we have, for example, this blue triangles. It's base classes, which nobody talks about. You use them for training, and you don't have a test set. You don't report accuracy on them. You use them for meta-learning framework, and then you adapt. You have already these episodes, small episodes, where you create from the novel classes, from this red squares, basically. And then basically you evaluate already your framework, which you train on the whole data set on your base classes. Let's talk about, like, this is the most common approach. It's meta-learning to train the framework, and where the goal of this framework is mimic FewShot episodes with the base classes. So base classes, we don't take into account the accuracy on them, but we mimic these FewShot episodes with these classes. For example, one of them, we can classify it in when we simulate, we use a prior on the data similarity. Basically, it's non-parametric classification when you have prototypes, and then you find the most similar classes to these prototypes. It's matching networks, prototypical networks, or you create it's a metric learning with relational networks when you learn a metric in the space. The other types of frameworks, it's on hypothesis space. It's the most famous, it's MAMO, where basically you learn the network adapt quickly to the new classes with the gradients. Or, for example, prior on data structure, where you learn from the base classes, you learn actually what can be, how it can be augmented, how it can be simulated and hallucinated. This shrinking and hallucination paper, it's quite old, it's from 2017, and they learn this transformation of the data on the base classes and adapt them to the FewShot classes. So many approaches which use base classes to adapt it on a FewShot samples. So, and in generalized, I'm working, and this work is connected to generalized FewShot learning. What is the difference? That instead of not taking account these base classes, we want to include them and also calculate their accuracy and how the model performs on them as well. Meaning that if we train our model on base classes and we use them to learn to adapt to new classes, we also want to take into consideration their performance of these classes. Yes.
Sorry to interrupt, but I see some form of green lines on the screen. Are you able to see it?
Yeah, I also see them. I actually saw that. I don't know from where they're coming from. I never seen it myself before. And maybe I can stop. Yeah. So basically, it's a generalized FewShot learning where we take into consideration base classes performance on the base classes as well. It meaning that for the trained data in each episode, we have also, again, very few samples from the novel classes, but during test time, we also we test our model, how it performs on not only on the novel classes, but on the base classes, which we had for training the model as well. So this is a difficulty. So usually people don't consider the base classes and how you have a lot of training data for each class in the base set, but very few samples for the novel, how the model should adapt there. So one of their approaches, which was introduced in 2019, that we have base classes, and again, it's meta-learning framework. Then you simulate the same situation that you have a lot of training samples per class on the base classes, and with the same classes, you simulate novel episodes. And then you train the network to adapt quickly to this setting. It works pretty well. But there is also recent work in 2020 where they show that when you have a good embedding, so it's called rethinking FewShot image classification, a good embedding is all you need. Meaning that if you train embedding with the base classes, like in the first, in the top of the slide, then if you take this network, which you pre-trained on the base classes, or it's ImageNet, if everybody knows the transfer learning. And then you classify novel classes just with the same network, and basically you fine-tune the network with these novel samples where you have only one image per class. Then is it good? Is it performing like on par with state of the art? And actually it is. And you also can apply some technique which is called distillation, when you distill knowledge from the previous classes, and it also actually improves the performance by a couple of %. But the point is that all these meta-learning frameworks, they work pretty good, but if you have enough data for the training samples and you have a good embedding, then it's good enough to be very performant on the FewShot cases. So we actually take this approach, and here I want to introduce the contributions of this work. First of all, we present a framework which explicitly addresses the problems with the generalized FewShot problem. First of all, we need to learn novel classes where we have very few samples per class. Second part is we shouldn't forget old information about the base classes if we learn them separately, how we do here. And at the same time, we also need to calibrate on the classifier level, because we have a lot of training samples for base classes and very few for novel classes. So how to calibrate, how to make this performing well on the both sets. We also propose normalization for cross entropy to learn and calibrate classifiers, and some constraints on the weights. And we show the SOTA performance, state of the art performance, and ablation study on different parts of the framework. So now I will go directly to the framework and to different parts, different phases. So if anybody has any questions so far?
I don't see any in the chat box, so I think we're good to go.
Yeah.
Good to go.
Yeah, thank you. So first phase, what we take all base classes and just basically pre-train our network, which we have here, parameter theta. We pre-train our network. It's usually ResNet 12 or ResNet 10. And we train classifier for the base classes. It's the first phase. It's basically the first pre-training stage, supervised learning, nothing special. Second phase, that's already some magic happening. What we have here, we have episodes. So we have, for example, one training sampler per class. We have 5 novel classes. For base classes, we have a lot of classes, 60, for example. And here we need to train new classes, new classifier for the novel classes, and at the same time, keep some information about the base classes. So what does it mean? That we take the approach that we fine-tune the model that we had here, that we trained on the base classes, and we update the parameters slowly because we're fine-tuning with new classes and also in supervised way. At the same time, we basically keep the parameters of the new model. We make them changing very slowly. It means that, for example, we can either lower learning rate, or in this case, we found that what works the best, that we have a constraint that basically keep the parameters of the model close enough to the old parameters, which we trained on the base classes. Basically, it means that we don't forget information about the base classes in the model. I think
Sure,
there is a question.
Yeah, I guess so. You can unmute yourself, Ashutosh.
Hi, just was confused what this arrow means. The double-sided arrow, the gray one, where it's written L2WC.
Yes,
So,
this one. This is
yeah.
yeah. This is constraint. Basically, that I have L2 constraint on the weights. I keep those weights, the new weights, I make them changing to adapt to the new classes, but at the same time, I constrain them not to change so much to keep these updates close enough to the old model. Is it answers to your questions? I guess so. So if you have any other questions, just unmute yourself. Yeah, just go ahead. I think you can unmute yourself.
Yes.
Yeah.
Yes, you can.
Yeah. Am I audible? Hello?
Yes, you are.
Now we can hear
Yeah.
you.
Okay. So this regularization part is used with this base normalized CE, which is being used
Yes.
to train the novel classes. And then we are
Mhm.
also restricting the parameters to be in a similar space where the way the parameters of the model one are. That's what we
Yes,
are trying to do.
exactly.
Okay.
Yes, yes.
Okay.
Yes, basically you're completely right. Of what we're doing here is that we train the novel classifier on the novel classes, but we train them not like when you apply cross entropy, when you have supervised learning, then you basically how you apply softmax over the classes, right? Over the logic when you have outputs, that you have your class, your output, and then you normalize them with only logic from your classifier outputs over your classes, over your 5 novel classes. What we do here is that we take into account that this classifier, which is from the base classes, is already learned. So it has already quite strong outputs. And their magnitude of these outputs is much higher than on the novel classes. And why we do this normalization here? So we won't have them on the same range. And this apparently, it showed that it's a very good way to do this, because it's taken in the normalization, it takes into account the magnitudes of this weight of this classifier, and it makes this logic stronger. And the novel classes accuracy can like the output on the novel classes is getting stronger than the outputs on the base classes. This blue outputs of this classifier. And at the same time, we keep this weight close enough to the previous weights, then that the accuracy on the base classes is not dropping like explicitly on the base classes, because this classifier we're keeping fixed because we anyway don't have anything propagated through it during this phase, because this phase includes only novel classes. So this is the main intuition behind this construction, why we want to have these classes keeping is they're close enough to the base from the first phase, and at the same time normalizing this part. Yeah, I'm glad that I guess I answered your question. Yes, this is the second phase, and then we have the third phase. In the third phase, we do calibration. Basically, I told you that we basically trying to emphasize and make this classifier on the novel classes stronger enough, and but base classifier kept fixed. So here, if we stop here, then we will have uncalibrated, very strong novel classifier and good performing base classifier, but only on the base classes. Now we want to have them on the same range. And at this moment, we subsample basically very few novel base classes from this set. It can be also one training sample per class. We don't need more. And then we do a couple of epochs when we fine tune the model and fine tune the classifiers to make them on the same range. So this is basically the same as the whole framework. We have 3 phases. In the first phase, we train on base classes. In the second phase, we're trying to learn novel classes at the same time, not forgetting base classes. And in the third phase, we calibrate. So now I actually will go to my favorite plot in this part. It's already going to the ablation studies. So this plot explains why we have each stage. So let's go from the first one. First of all, I will explain the classification protocols here. First, we have NG and BG. It means that it's generalized, and we take into account both classifiers together. We have space, common space for the novel and base classes. And NG means that we test only novel classes, but with the 2 classifiers. It means that we have outputs. If we have 5 novel classes, 60 base classes, then we have output 65, the whole space, and then we're basically choosing from them. For the PG, we have the same, but for base classes. NN means that we take into account only novel classifier, we only take into account 5 outputs, only for specifically for novel classes, and it means that it's accuracy like for general and standard FewShot case when we test only on novel classes. And BB, it means that we test only base classifier, only on base classes. So let's look at the plots. First of all, this one, the first one. When we don't have normalization and we don't have constraints, how it behaves. First of all, I don't show here the first phase. This one, this is kept fixed, and we have a good pre-trained model and good performance on the base classes as a classifier. We keep it for granted, and this starts here, so it's about 80% accuracy on the base classes. How it behaves further? In the second phase, what's happening that we getting accuracy, like novel classes getting started to learn something, but at the same time, we lose accuracy on the base classes. The model forgets about the base classes, and it's dropping basically to 0. And in the third phase, when we have both sets for the base and novel classes, novel class accuracy drops very fast because we have very few training samples. And this is very fragile state of the model, and it's very easily disrupted. And actually the base class is getting higher, the accuracy in base classes, because the model was pre-trained and it's seen a lot of training samples. So this is how the model behaves when we don't have any constraints. Then we go when we have a constraint on the weights. It means that we want to keep the model as close to the base classes, performance to the base classes as possible. Basically, we have constraints, L2 constraints, we see. And you see here that we still can learn something on the novel classes during the second phase, but we keep very high accuracy on the base classes. And then when we have again, and we don't have any base classes in the second phase, we have only in the third phase, when we introduce base classes training samples, then the accuracy goes again very high. If we see this dashed line, it means the accuracy only on base classifier with the base samples. And it's getting very high back when it was before. And the novel classes, it's dropping. So we need basically our purpose, our goal is to keep this solid line, red and blue, high. So let's see now how it performs when we don't have constraints on the weights. We allow the model to adapt quickly to the novel classes without any constraints. And but we have normalization in the common space between base and novel classes. This cross normalized, base normalized cross entropy, this constraint. Then we see that base class is dropping very fast. So it means that I remind you that novel classifier in this case getting much stronger than the base classifier. It's happening exactly here. Then base classifier directly goes down. And novel classifier, their performance is actually better than without. And it's getting high numbers, but then when we introduce again novel classes and base classes together during the third phase, the rate of the drop of the novel classes is very high. And at the last, when we have both base normalized cross entropy and constraints on the weights, it means that during second phase, we have constraints and the base accuracy doesn't drop much. And accuracy only on base classifier, we keep high. And at the same time, their novel classes can learn very fast and getting stronger performance because it also influences their classifier weights and magnitude. And then when we have during third phase, both base classes and novel classes, it can recover quickly for the base classes back to the way it was before. And at the same time, it's not dropping so fast. Basically, it means that we can balance and calibrate it more or less much better than before. So this was our goal, actually. So are there any questions so far? Yes, not really. Okay, then I will go further. So the first question would be, do we really need all three stages? Can we get rid of the third stage, for example? Do we need this calibration? Can we keep it only with the novel classes with the calibration? And partly yes, so we can still have good performance when we have constraints on the weights, and then when we perform well the novel classes. But what you can see here is that on base classes then it drops further, because we don't have anything to remind the model how it should perform the base classes in the joint space, and it learns more novel classes. So basically when we have the two, all three phases, then it performs much better, then it can recover on the base classes much better, and we still can keep very high accuracy on the novel classes. And we compute the accuracy on as a harmonic mean between the two to find the trade-off. So what if the question, if we skip the second stage and directly go to the third stage when we have the balanced set and we calibrate together with the base classes and novel classes, then what we can see that actually novel accuracy, just novel accuracy, this is this one, basically when we have only novel classifier and the test on the novel classes. This is standard FewShot learning accuracy. It's getting very high during the third phase as well. But classification is a joint space with base and novel classes. It is much lower, and it's can't because base classifier it's very strong, and it can't outperform it. So we need second stage to make the third classifier much higher. Yes, it's mini ImageNet. They're all ablation studies we did on mini ImageNet for the evaluation, for the comparison with SOTA. We made much more. We use much more data, much more different data sets. I will go a bit to this later. Yeah. So, and here we compare what kind of constraints we can also use here to keep base classes higher. And we have our constraints on the weights. Another option, previous table is one more. This one, the higher one, without the third phase. Yes, sure. Basically, what we have here, we're studying if we need this third stage at all. Like we only stop if we stop here on the second stage, like here, for example, here, and maybe we can stop somewhere earlier, and maybe we can keep base classes higher if we increase constraints on the weights. If we need this calibration stage at all. And basically this table shows the strengths of this constraint on the weights. So if we keep this constraint stronger, then we keep base classes much higher. And you see the accuracy on base classes increases. But at the same time, accuracy on the novel classes is starting decreasing from some moment. And then if we keep this even higher, then accuracy on the novel classes go even down more, and on base classes it increases. But with the third stage, it's an autoparameter. It's basically these different types of classification protocols that it's in the joint space for the novel and the base classes. Then we consider the joint classifier. It's basically a concatenation of the two classifiers. And then we compute their accuracy, not only particularly for novel classes, but for novel and base classes together, like here. Yeah, and yeah, no problem. Thank you for the question. Here we see that actually when we have this calibration stage afterwards, then we can increase the accuracy on the base classes, and at the same time we keep high accuracy on the novel classes as well. I want to note that actually accuracy on the novel classes, if you look at the FewShot standard protocols on the, for example, mini ImageNet for 5-way one-shot, then it's actually already much higher than now, that the performance rising with each conference. But at the same time, we have state-of-the-art performance on the base class as well within generalized few-shot learning. In this table, we study the influence of how to keep the accuracy on the base classes. Can we use something else instead of having these constraints on weights? One of the common things, which actually at this moment, it's very popular within different fields, it's a knowledge distillation. It means that when you have pre-trained model, and instead of constraining weights, you have you simulate your data, your outputs with another type of data, and then basically propagate these weights on your outputs of your classifier as you have your original data. And as much, it's very popular with incremental learning, and it's also getting popular in different fields for keeping knowledge or improving the performance. So we tried it here as well. When we have like the first one, it's when we have on very few samples, when we have, for example, one training sample per class on the base classes, and then we use this knowledge distillation. It's very, very few training samples, and it's actually not performing well at all in this case. So then we thought usually it's performing good when you have a lot of additional data, and then it's knowledge distillation plus, and we use much more data there. And in this case, actually, we see it's performing very well. We increased very much accuracy on the base classes, but at the same time, this preservation doesn't work well for novel classes, and it drops a lot. Yeah, so we figured out that actually this constraints on the weights performs the best in this setup. Yeah, so another part is how much we can keep from base classes. It's basically these ablations on the fact which lambda we can use for this actually weight constraints, and how much we should keep them. Like, can we keep them more? So if we increase lambda, then we have much higher accuracy on the base classes, but it's a trade-off. In this case, the accuracy on the novel classes starting dropping at some moment. And basically, this region works the best for this framework. Then we can keep high accuracy on the base classes, and at the same time, we keep accuracy on the novel classes high. The same for the different setups works. And it's basically how to choose lambda, how much to keep to constrain weights from your base classes model. Yeah, actually some technical details which I found interesting, that it's also written in some papers from time to time. Basically, when you have a transfer learning you have some pre-trained model, and then you have another data set or another set of, in this case, novel classes. It works much better if you freeze patch norm, even it's within the same dataset, because it was the same dataset, mini ImageNet, and base classes and novel classes, just different classes from the same dataset. But still, freezing batch norm helps when you freeze it from the base classes, and we show it also here as well. Another part here, that it's very popular to normalize classification layers in the few-shot learning, and using or not using bias. So we found that in this work, because we have this cross normalization with base normalization, then we don't need normalize additionally our logits. And actually, without bias, it works slightly better, but I think it's not very much difference in the performance in general. So now I will talk about comparison with the state of the art. It's on mini ImageNet with the different settings with different types of networks. This is Con4 versus ResNet 10. And we can see here that what was on the previous state of the art, that basically on the novel classes, they had much worse performance than we are, but they had much better performance on the base classes. So what we did here with the calibration, that we increased the performance on the novel classes a lot. And it's also, in this case, we improved the accuracy by 3% on the harmonic mean, even like by 4%, while we a little bit dropped on the base classes. We can see the same trend on the another setting, 5x5 shot, that we increased a lot on the novel classes, but we here we don't drop on the base classes, we perform on par. And at the same time, harmonic mean accuracy, it rises a lot. When we increase accuracy on the novel classes, it means that we have better trade-off. Yes, actually, this is all for generalized FewShot learning. Look, that I'm very sorry. You was asking, like, there was a question about the data sets. I didn't include other data sets because we have the same tendency on other data sets for generalized FewShot learning. We did experiments on the tiered ImageNet, also on video data sets like mini kinetics, UCF data sets. And we also have an extension for incremental FewShot learning because the tasks are very similar. In general, that you have base classes, you have a lot of phases, a lot of sessions for incremental FewShot learning. And then you have first is the training phase, it's the first phase with the base classes. And then you have new sessions from second to third, fourth, and so on the novel classes. And then you have very few training samples per class. And what the essence of it, that actually you have increasingly long, you increase your classifier with each session. If you had first session, it's 60 classes, you need to classify. During second session, you need to classify 65, then 70, 75, and so on. Each time with each session, you increase it with 5 new classes. So how we do this, that we use first phase, we plan the training set and the train on the base classes. Then you have a second phase with a second session when you have 5 new classes. Then if you want to evaluate, then we use third phase for evaluation. Then we apply third phase for a couple of epochs and evaluate. If we need to continue with the sessions, then we apply again second phase. Then if we need to evaluate, we again apply third phase. So in this case, we still can keep accuracy very high on the base and null classes in the new task. It was introduced, I think, 1 or 2 years ago, and there's already some works there. So what we have as a result, if you can see here, the overall harmonic mean, we compare with previous work, and we increased for the second session, increased a lot. And we actually increased a lot for all the sessions by at least 10% or even more. When we have increasingly number of classes, 5, 10, 15, and so on. If we just use fine-tuning during training, so we have base classes, and then we fine-tune the model on the novel classes, first session, second session, and so on, then this is accuracy, and it's getting lower and lower because you forget about the base classes, you train very poorly on the novel classes, and so on. And you actually, here you evaluate accuracy on the boss in the joint space. So what else? We have separate accuracy on the base and novel classes. It means for each session, if you can see here, actually accuracy on the base classes in our case drops compared to the all previous state of the art, because we have this trade-off, we calibrated. But at the same time, we increase a lot on the novel classes because again, we have these constraints during second phase, and we force the novel classifier to be stronger than the base classifier. That's why we improve so much. And this improvement on the novel classes leads to the improvement overall. That's why we perform much better than the previous state of the art. Yeah, so basically, I want to conclude here already. We first of all define the problems for generalized FewShot learning. We define what are the problems here, what are the issues, that it's novel class learning, catastrophic forgetting, and classifier calibration. We propose our framework to solve these problems, and we state the very simple approach, and we propose a benchmark for these types of problems. We also connect generalized FewShot learning with incremental learning, and we achieve the sort of performance on all the respective tasks. That's all for you, all from me. Yeah, thank you for attention.
Thank you so much, Anna. That was a detailed presentation. So anyone in the audience who wants to ask question, please raise your hands and we'll unmute you. Till then, I have a question for you. So we, like in the past few papers that we have discussed, everyone wants to know the journey of a paper. So I really wanted to know, how did you get the idea? Did you start with FewShot first, or the incremental learning was more of your focus? And like, how did you develop upon it?
Yeah, it's a great question. Thank you. Actually, like initially, when I came to the group and we were discussing their ideas where to move, we came up that it's interesting to go with the FewShot learning, and then we came up with ideas that basically FewShot learning, in some different aspects, they are already saturated, and we wanted to solve something new, something interesting, and we came up that this is actually generalized FewShot learning, which not a lot of people touches it, so we went to this direction, and it was some months of exploration, what should work there and how it should work, and I felt that it should be some calibration on the weights, but it was once I was talking with some people around, and eventually I found out that actually this is the way how it should be, and it actually worked very well in this case. And yeah, I consider this, I like this paper. It's not always the case that you like the paper like from the beginning, and during writing I really enjoyed writing this and develop these ideas.
I see. And how long did it took you?
In general, I think about like 8 months or so. Actually, I think first one, we submitted it to CVPR, the version of the paper, but then like after 1 week, when I was preparing supplementary materials and like I was creating some confusion matrices and so on, I found that I had a bug in my code, and we basically it was shame, and we had to withdraw the paper, of course, because it's not on the state to submission. Then I spent like a couple of more months on the development, and we submitted already to ICCV. Yeah, and so in general, I think it took me about 8 to 10 months initially from this going back and forth.
I see. Okay, there's an interesting question in the chat. Devraj is asking that he has a general question for FewShot meta-learning works. Why generally algorithms are not evaluated for more than 5-way, like 8-way, 10-way, 15-way? Was work like MAML evaluated for these high N-way K-shot learning? I was wondering how MAML performs on large N in N-way. Any suggestions on that?
Yeah, thanks. It's a good question. Actually, it's not because this is the most standard and settings. 1-way and 5-way. 5-way. It's the most general setup, and then you have how many shots. Usually, it's 1 shot. Like how many training samples per class you have. Either you have 5 new classes, and each class has 1 training sample per class, or you have 5 classes and you have 5 training samples per class. And when you have more classes, more new classes, then it's much more difficult task, of course. And actually, there are quite a few papers which getting into this and evaluating on more different settings and more classes. So I agree that it's very interesting setup. And actually, I evaluated. I'm not sure that I put the results directly in the paper, but I definitely evaluated different setups on 10-way, and I think I have a supplementary material, 10-way and 20-way new classes. And it's usually supplementary materials or some ablation studies. So nobody really compares as a state-of-the-art performance on them. I think it's just what people used to. Yes, but I agree that it's also one of the directions which people can work on, and like to make their algorithm stronger on more new novel classes.
I see. Okay.
Hi, Anna.
Yeah. Hi.
Yeah, we were looking at class incremental FewShot learning, right? In this case,
Mhm.
is it always necessary that it should be done in a supervised setting? Can we do it in unsupervised setting? Because incremental learning, is it always the case that it is supervised setting? Can we do it in unsupervised, where let's say we are not aware of the ground truth labels?
Yes, but can you specify then? Because I think, yes, I mean, basically it's a research. You can do any interesting task. But what do you mean exactly about the unsupervised way in incremental learning? Because
let's say we are doing incremental learning with respect to weather domains, and we have pre-trained model and daytime images, and we are trying to adapt to changing weather conditions incrementally. So, but we are not aware of the ground truth. But we are not aware of the ground truth information.
I think I just had an interruption. Can you please repeat the question and your thoughts on this?
Let's say we're doing incremental learning on changing weather conditions. Okay. So this is domain incremental continuous learning, right? So, and we have a pre-trained model and day images, and in the second domain, let's say fog domain, fog weather condition, we only have the images and we don't have the ground truth information.
So you mean to classify you have in U5 classes, but you don't have ground truth table, but you still want to classify, and you want to, I think it's more closely to OpenSet problems. Basically, it means that you have some classes which you know, and then you have some new classes which are coming, and then you need to distinguish either it's from your previous classes or it's in new classes. If it's a new class which you haven't seen before, then you need to classify it as well in some cluster. And it's really this type of problems, it's called OpenSet, and there is also a lot of variations in terms of how you define exactly your problem and how you solve it. I haven't worked on such problems myself yet, but I also consider they're very interesting, and but it's very challenging. Yes, I like the way how to do some unsupervised classification. It's some clustering, I would say, but I don't have a solution right now for this problem. And first of all, it's I think it should be defined properly, like to basically work on this, because one of the solutions of the problems, it's basically how to state the problem, and then you can already derive a solution if you properly can formulate it.
Yeah, one more issue in that case will be how to define your competitors, like what should be Shota in that case, because you are ideally defining the problem statement in that case. Yeah, thanks for that.
Yeah, thank you.
I also I'm not sure if we discussed it and I missed it. Do we have a case of domain shift, or did you explore the domain shift between the base class or the novel classes?
No, in this case, I haven't explored it, but actually I did some additional studies myself. It's not in the paper, that basically if you have very different base classes and novel classes, basically you have from one set this environment base classes, and then during novel classes you have, for example, just dogs. So quite big difference. What are the changes there? And basically in this case, it makes sense how much constraint you have on the base classes, and do you need to constrain them more or not. But more specifically, domain shift, domain adaptation, we haven't studied here. But actually, I'm also have some projects where I'm working also on domain adaptation right now. They're also very interesting tasks.
I see. Interesting. Yeah, so this is there's one more in the chat box in continuation of the mammal question that we were having. So the question asked that how does mammal performance degrades with the large number of classes?
Unfortunately, I can't answer on this question. I haven't worked directly with mammal myself. I never did experiments on this type of approaches, and therefore I can't really answer nicely. If you can contact me and we can study, I can look it up, and I can talk to people on this topic as well.
Definitely. Sure. That's fair. Okay. Do we have any more questions? Because, okay, yeah. Okay. So related to the paper, these were the questions I had to you. And yeah, the audience also, we're really glad that you agreed to present on such a short notice, even like when the time was shifted around. There are thanks pouring in the chat box. So yeah, I'm also very, very thankful for the presentation. Thank you, Anna.
Yes, thank you very much for the invitation. I'm really happy that we eventually made it. And yeah, thank you.